Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, today we deal with, actually we are done with this part, okay? So we are dealing inside scan generator. We are done with the RE to Nfa, Thompson's constructions, all those things. We saw a lot of examples of Nfa as well. And now it's time to convert Nfa to Dfa. This is what your scanner generator does inside. Now you may wonder why, because Nfa is easy to build from the RE, okay? But when we talk of computers which have a deterministic nature, so Nfa is no good, because it has the non-deterministic attires. So we want to get rid of that non-determinism and be more on a determinism side. Even though Dfa has a much higher number of states than Nfa, but we can minimize it using the algorithms, okay, to make it minimize the Dfa. And Dfa has the deterministic nature, which we actually like, and we can convert that easily into some kind of program, because we want to go on a programming side, the computer side. So we want more determinism. This computer is more deterministic, okay? It's like deterministic. So we have what's called the subset construction. So actually in this video we will learn about this subset construction, where we convert from Nfa to Dfa, okay? A Dfa actually is an Nfa with a few restrictions. So the language Nfa represents, the Dfa represents same language, okay? In Dfa we have no epsilon transitions. This is the first thing. You must be knowing these things in your third computation, but if you don't know, I'm giving you a little bit more. And for every state S, there is only one transition, okay? So there's no multiple transitions like we had in the Nfa. That is, on state X, on taking X as an input, you go to a one state only. A Dfa is easy to implement with an algorithm, and it has a deterministic behavior. That is why we are doing this. Now when we say Nfa to Dfa as a subset construction, basically there are three main cases of non-determinism in Nfa. First, as we saw, transition to a state without consuming any input. So you don't consume any input and you transit. Epsilon transitions are there, so you want to remove them, okay? We have multiple transitions on the same input. You take one input, okay? Say for example you're on a state and you take input A, you go to one state, you can go to the same input to the another state, or other state as well. So that means there's a multiple transitions, as we saw in our examples in the last video. Or there is no transition on an input symbol, okay? There may be no transition at all on some input symbol, okay? So these are the three things we have as we know them already. So to convert Nfas to Dfa, we need to get rid of non-determinism from Nfa, simple as it is. So using a subset construction method to convert Nfa to Dfa, it involves actually following steps. We'll take care of, firstly, for every state in Nfa, determine all reachable states. We have to see which states are reachable, because in an Nfa we may have many states which are not reachable, so we will leave them. We will not take them in a Dfa. So you have to talk about all those reachable states for every input symbol. Now there may be a set of reachable states which constitute a single state, okay, a compound state in a converted Dfa. So each state in a Dfa corresponds to a subset of states in the Nfa. So you may have, for example, we'll see this more in example, you understand, but let me give one example and to comprehend. Look at this example. Now this is an Nfa, and there are some epsilon transitions from 0, 1, 2. So if you are on 0, you can go to the 1, you can go to the 2, you can go to the 6, and from 2 you can take the 8. Basically, so if we take a state in the Dfa like 0, 1, 2, 6, 8, okay? So 0, 1, 2, 6, 8, okay, these guys, because on these guys you can go on an epsilon transition. So this basically in NFA your 0 was your initial state. Okay, this was our initial state, state 0 in NFA. But in DFA we have to find the epsilon closure. What does that mean is you just see on epsilon where you can go. Okay, you can go on a 1, you can go on a 2, you can go on a 6, you can go also from this way to the 8. So these whole this 0, 1, 2, 6 and 8, they become a single state. That's our start state. Okay, and then on A, we are talking then on A, actually from this 2 in NFA, if you take an input A, you go to the 3. But here, because this is whole as a one state, so if you take A from there, you can go to the 3. Okay, does it make sense what I'm saying? So this is the example you can take. Actually here is missing, this is C here. Okay, here is a C transition. Yeah, here we have C. Okay, now so 0, 1, 2, 6, 8, 0, 1, 2, 6 and 8 on A goes to 3 because this whole thing is as a one state. If I change the pen and make it the red area, this whole thing is now a single state, right? It goes from this as well, 8 also, and 6 and this. The red area is a one state now because of the epsilon closure. Okay, then when on a C, and this thing on a A goes to 3, and on C it will not go to 7 only, because then epsilon transition will go to 5 and also to the 8 and right. So we may have in it 7, 5 on C, 7, 5 as well as 8. Okay, then from 5, okay, actually it goes on epsilon closure to the 1, and from 1 you can go to the 2 and 6. So these all guys here are actually the one state. This is what we say as a compound state, right? Okay, so this is what we say here, that the set of reachable states constitute a single state. So this represents a single state in the convoluted DFA. Each state in the DFA corresponds to the subset of the states in an NFA. This is here you can visualize that. So we have to find the reachable states for each new DFA state until no more new states can be found. This is what I say is, we do it in an example, you understand it properly, that we are saying that we just see the state. Say for example we saw this state and we see what is reachable. This guy is reachable. Okay, the moment we found the new state, and we try to see what other states are reachable from this state. Okay, if for example some state is there and we are not having the reach to that, no access to that, so that will be eliminated as easy as possible, right? And all these epsilon transitions are also eliminated because they are considered to be as a one state. So why we use NFA? Because they are very easier to express language than the DFA. This is the prime thing why we actually use the NFA. As you can see here, just see the simplicity of this language, okay, which NFA represents, and and the complexity in this case, and the same language which is accepted by the DFA. Okay, or you see this example where the machine 1 has a language which actually 1 0 star accepts. This is the 1 and 0 and any many and in absence. So this is the acceptance state, initial state. And in case of DFA, the same thing can be presented like this, that you have 1, go to the Q1. Okay, then if you have 1, you go to the death state because after Q2, if there is 1 or 0, it dies out because there is no output. So this is the death state in case of DFA. We know them. And from Q0, if it is a 0, it starts from the 0, it goes to the death state. And if it starts from the 1, then only it can go to Q1, and if after that is 0, it goes to the acceptance state. So both of these guys actually represent the same language. We should also understand the language accepted by NFAs are actually the regular languages. We will talk about these languages later on in our chapters. I will give you one picture to let you understand where in languages we hold, and the other language accept the DFAs as well. Okay, because DFAs, NFAs, they accept other languages. NFAs and DFAs is the same competition power, and accept the same set of languages. So really, there is no such thing that we will miss out in DFAs and NFAs. So they are actually accepting the same languages. We can have a language which can accept the NFA. The same thing will be done by the DFA, and they have the same competition power as well. So every DFA is truly actually an NFA, right? What that means is any language accepted by DFA is also accepted by NFA. Okay, now let's take up the complete example of subset construction. So we'll go in detail now. So we say that we have an NFA, okay, with states, say for example Q, and input say sigma. Say for example we have some states A, B, C, D maybe, and the inputs are say for example small a, small b, and transition function delta n. We know that start state is Q0. So out of these states Q, we have one of the states as start states, and there may be final states, set of final states F. Okay. Then we got to create a DFA which can have a states 2 raised power Q. You should understand, if we have a Q states, DFA has a huge number of states, that is 2 raised power Q. That is actually the set of subsets of Q. Okay, that's why we go for the minimization of DFA then later on. Okay, if we have more states, we can do that, not a problem. Then it also has an input of the same sigma, and the start state of the DFA is same as the start state of the NFA. This is the point to be noted. And final states, when we talk about, is say for example we have some state which is the final, and wherever that comes in the DFA, that state becomes the final. We will understand it with an example. I will come back to this point when it will be an example. You will understand it properly there. Now in DFA, we actually may have the set of states, okay, of the NFA states. We make a set out of NFA states, and that will become a one DFA state, and that may have a name. We can use a name. Say for example there was a state 1, 2, 3. We collected them together of the NFA. State 1, state 2, state 3 is bundled together. Maybe we call it as an A now. Okay, maybe we call this state as an A. So we rename the states. Okay. So we may have a state like for example P comma Q. That means 2 states of NFA bundled together. Okay, so these 2 states are read as a single symbol, not as a set. Okay, now we have here 3 operations. Okay, one is the Epsilon closure on some state S from an NFA, and then there will also be the Epsilon closure of some T, that is when we have a set of states from the NFA. We may have one state from NFA, then we may have a set of states. So for example, we have a state 1 in the above example. We see here here, if we are talking about the 0 and we see epsilon a closure from this state, that means all those states which can be reached from the 0. Say for example you can reach it from the 1, you can reach it from the F. Now you may have then a set 0, 1, 2, 6, 8 as a one set, as a one state, and you see on epsilon closure where you can reach from these. So you have 2, and then you have also the third operation, that is on some input symbol. So for example here is an input symbol A or C or whatever input symbol is, where you can go to that input symbol from. So we say that we have here the what's called as a move. That means we have a move operation. That means you are moving from the T, whatever that T is, on A wherever you go, because you have to first see the epsilon closure on those sets, and you see that, and then you see on A wherever it goes. Okay, let's take a simple example first where we don't have epsilon moves. Okay, then we see the more complex example of epsilon move, and we see that we have the initial state is same as the final state, sorry, initial state of NFA, and final state is anywhere we have a state, final state in NFA, that will become the final state in the DFA. We'll see that also in an example. Say we take an example of, as the popular in the books is, the second symbol from RHS is 1. Okay, so how we do that? So we say that, hey, this is my start state, this is say Q0, this is my start state of NFA, and in the beginning, if I have a 1 or 0, I don't care. Say if the sigma here is 1 and 0, we should know what is our input alphabet. Okay, now there may be 1 or 0, no problem in a Q0 state, first state. Then moment it goes the second state, so this is the second from the RHS, is that means second last, that this guy. After that it may be 0 or 1, that is not a problem. And if this is the second last, then this is, I'm gonna accept it. So this is my Q1 and this is my Q2, right? Now, and this is my second last symbol here. So this is, if it is 1, I'm gonna accept it. In the beginning, if it is 0s or 1s, no problem whatsoever. So if the moment I got the second last symbol 1, so I can take any many you know, or what will be in my language will be all those things. For example, I take 0 0, okay, and 1 0. If I take like this, for example, okay. Now this is second last. It's 1. I will take it. Okay. Say for example, in the beginning it came 0, it goes Q0, again 0, it goes to Q0. The moment it goes 1, it goes here. After that, if it is 0 or 1, no problem, it will accept it. And similarly, if it is, for example, 0 1 1, it's going to accept it, isn't it? So because second last is 1, it's going to accept it. As you can see, first symbol 0, it goes to the Q0, then it's 1, it goes here. After this 1, it goes here, accepts it, and so on. Whatever, we know that. So this is my NFA, and I want to convert this into the DFA. The first thing I will do is I will make an Nfa transition table, and then I make a Dfa transition table. Okay, so we first make an Nfa transition table. Let me choose a different pen. So what we have actually here is, this is Nfa transition table. Okay, TT I call it. Now this is here. Now what we have here is like this. We have here firstly on this side we have the input symbols. What is that? Input symbol is 0 and 1. That's alphabet. And then we have a states. We have Q0, Q1, and Q2. That those goes here. Q0, Q1, Q2. The transition table, as you know, is very simple. Nothing new. We have done it already, right? Okay. Let me change the pen now. We'll make it some blue. Okay. So where is the Q0 hitting? On the input symbol 0, right? And we see here that, okay, they are going somewhere. And now when we see here the Q0 on the 0, it comes here to the Q0 only, right? So it goes to the Q0 only. Q0 on 1, where is on the 1 it's going? So it's going on a 1 to the Q0 as well as to the Q1. So we write it in a braces that it goes to the Q0 as well as to the Q1. Now this thing is read as a simple state, as a one state, right? We'll see that. And we also should note down that which is my start state. Q0 is my start state, so I will start it here. And which is my final state? Q2 is my final state, so I will say star to the final state, right? Now wherever the Q2 comes in the NFA, so because Q2 is a final state, and wherever the Q2 comes in a DFA, those all states will be the final states, and Q0 is always going to be the initial state, right? Now from Q1, sorry, Q1 on 0 goes to Q2 only, and Q1 on 1 goes to Q2, right? And whatever Q2, now Q2 on goes nowhere, so they are the empty set, the 5, then they go nowhere, right? So this is my transition table for the above transition diagram, which is of the NFA. Now I have to make the DFA out of it. So I will make a DFA transition table. So I will make a DFA transition table, right? So how I do it is I will make my choose my pen, different pen. Okay. Now here I will say here firstly the NFA states, the states I had from the NFA, right? Then I have the DFA states. Then I have the DFA states. Okay. Then I have here the next next states, and that's what the input symbols we have. That is 0 and 1, right? Okay. Now we will keep in mind all those points we have discussed. Okay. Let me change the pen again. Make it blue. Now firstly, the initial state of the NFA, that is Q0, is going to be same in the state in the DFA as well. So I say here Q0 is my state, which I am talking of right now. Okay, from Q0 where I am going, I am going to Q0 only. Okay, let me call this state Q0 as an A. Okay. So in DFA I am calling Q0 of NFA A. That's what I said. We rename the states in the DFA, right? Okay. Now from this here, now I see on 0 I am going to Q0, right? That I have named as A. Okay. And on 1 I am going to the new state which is the Q0 Q1. Let me call this new state Q0 Q1 as B. So I am going to B. Okay, I'm not taking all the whatever the inputs I have, because I have to go only wherever I can reach. That's the point. So I am from Q0. I am saying I need to rename it as an A. Then on 0 I go to the same Q0, that is the A, and on 1 I go to the new state called B. And what is B? Now B is, I will take only those states. Now here on I will take on only those states which are new to me. So that means wherever I have reached. Now I have reached to the state B. Now I have to see where I can reach from the state B. So I'm not going to interest in any other states, because there may be many states which are not reachable. So I will leave them out. Okay. So in this I have reached to the B. So in this case the new state is the B. So I will take that state. So what is firstly in NFA that B? The B is Q0 Q1, right? So I call it as a B. In DFA I call it as what? B. Now I have to see from the Q0 Q1 where I can reach, because now this is the epsilon closure of T. Like we said, we have to see the epsilon, because here are not epsilons. So what we have to see, move. We have to use move our from this state T on the input symbol 0, the third operation which I was talking about, right? That is, did I wrote? Yeah, move on the T with the input symbol A. So now here the input symbol is 0. So I have to see where I can reach from Q0 Q1. Okay, on taking input symbol 0. Now I have to take these two guys together. That's Q0 and Q1. That means these two guys have been taken together, and we're going to see on 0 where I can reach, because from Q0 I can reach taking input symbol 0 to the Q0, and from Q1 I can reach the Q2. So after saying where I can reach from these two guys, I will say I can reach to the Q0 Q2. So I will reach here to the Q0 Q2 on 0. So that is going to be my new state, and I call it as C. Simple, because this is a new state. Let me call it here, because that is Q. In fact, that is I can go to Q0 Q2. Yeah, Q0 Q2. So that is my C. Right? So I'm saying on Q0 Q1, if I take 0 as an input, I have reached the new state of DFA called as C, and C in fact is a set of states Q0 Q2, as seen here, Q0 Q2, right? These two guys. Now after that I see on Q0 Q1, on taking input 1, where I can reach, that is Q0 Q1 taking the subset of these two guys, and I see where I can reach on the 1. So I'm seeing I can reach from 1 is Q0, Q1, Q2. So that's a new state, so I call state as a D. So let me write the D here, that is Q0, Q1 and Q2. Right in a brace, because this is a new state, right? The D is a new state. I'm done with this. I should also tick whenever I done. I take it. Okay. In fact, when we talk about algorithms, we tick when we take the B. We actually mark it. That we are doing the B. So we are doing the C now. So we mark the C. Okay, C state. That is Q0, Q2. So now I'm talking about the Q0 and Q2. These two guys. In combination of these two guys, I will see where I can reach on a 0. Now when I say Q0 and Q2, okay, on 0, taking 0, I reach here is Q0 and phi, union of these two guys. So that's only Q0. So I can reach Q0, and Q0 means in Dfa what? A. As here we have seen it, it's an A, right? So I'm gonna write here A. So I'm reaching to the this is not a new state, so I'm not gonna take it here. It's already done. So I will write here only those states which are new here. That is where I have reached. Okay, so I have to see where I can reach from those states onward. A is already seen, it is done, so I'm not going to take it again. So from Q0, Q2, that is C, where I can reach on taking 1. So Q0 and Q2, right? These two guys. On 1, I'm going to reach to Q0, Q1, phi, that is Q0, Q1 only. What is Q0, Q1? I have already done. What is that? That's B. Yep. So we will go B. B is already seen, so we'll not see it again. Now C is done. So we take up the D. Now D is the set which takes all the three together, right? All the three. Q0, Q1, and Q2. So we have to see on 0 where we can reach on the 3. So I can reach Q0, Q2, and phi. That is Q0, Q2. Q0, Q2 is already there. That's called C. So I will say I go to C. From D, on taking 0, I go to the C. So similarly on 1, I'm going to go to Q0, Q1, Q2, and that is again the D. So on D, taking 1, I go to the D back. Now I got the transition table here. It is simple to make a diagram out of it. So right, we have states A, B, C, and D. So this is my state A. This is my state B, for example. This is my state C, and this is my state D, right? Okay. One more thing, I was talking, that start state is the same as the NFA. Okay, in NFA we had a Q0 start state, so this is going to be my start state, and the final state will be all those states which has the Q2. That was the final state in NFA. In Dfa, wherever the Q2 is, that's going to be final state. Now Q is here, right? So this is going to be my final state. Q2 is here. This is going to be my final state. So C and D both are the final state. So I say this is my A, this is my B state, this is my C state. The C state is a final state. We should understand that. And say D is also a final state in the Dfa. So right now, when I say A, B, C, and D, they are the different names we have given. And in Dfa, actually the state Dfa. The state in a Dfa is actually a subset of the states in the NFA, right? So it's a set. The B, if you see, is a set of Q0 and Q1. There are two states in the NFA, but here it's a single state. Now we have to make arrows from Q0, that is A, on going from 0, I go to the same state called the A, and on 1, I go to the B, right? Okay. Similarly on B, from B on 0 I go to the C. So on 0 I go to C, and on 1 I go to D, right? Now I take up the C. On 0 I go to A. On 0 I go to A, and on 1 I go to D. Similarly from D I go to C on 0, so I go back, and on 1 I go to D only, so I come back here. Now this is the equivalent Dfa of our NFA using the subset construction, right? Now we take a more complex example where we have also the epsilon closures. Let's take up this example which we have seen in the NFA video of examples, right? Where say A dot B or C whole star. So we actually made the Thompson's construction, and we have made the diagram out of it. So if you are not if you have not seen that, see that first and come back here. This is the NFA for this guy, where you say A dot B firstly, that means A and B, that's A then B, right? Concatenate them together, then OR with the C. So when you say C, C itself is this guy right here, it's a C, and then we say when we OR them, we use the epsilon transitions from state 7 to make it the OR this much, right? And then when you want to go for and we also want to make a final state. This was our final state at that moment. And then when we say star, we say this is not a final state, make a separate final state. Okay, go from the initial state and make a separate initial state. From initial state to the final state, go to epsilon transition, because stars is also the null. So because we may have nothing, so then you go directly from 9 to the 10 on the epsilon, and this one also has an epsilon move from here, so that can take it many times. So that make it the star, right? So we have done it already. We know these things, and now we want to do the subset construction of this guy, right? So how we do? First, we make the transition table of NFA. Then we make a transition table out of that as a Dfa transition table, and then we make a Dfa as a diagram. Okay, state diagram. This is how we do. So let's go for firstly the transition table of this guy, but this one have one additional input that's called epsilon. So if we make an NFA transition table, firstly we see what kind of states we have. The initial state is 9, so I will write it 9. Okay, then we have 7, for example. You can take it any order, not a problem. 1, 2, 4, 5, 6, right? 7. 7 is already taken. So we have 8, and then we have 10, right? So this is what I take: 9, 7, then 1, 2, 4. Then I go to this side: 5, 6, 8, and 10. These are my states on the left side, and on the right side we have here on the top are the inputs. I should say this is a small a. Sorry. Okay. This is B. This is C. Is small already. So this is epsilon. We have also the epsilon moves here. So we will see from the 9 on taking input A. Okay, from 9 input A, because this is here, right? So I go nowhere. So on 9 I'm taking input A, I go nowhere. On B I go nowhere. So this is 5, and C I go nowhere. But on epsilon I go to a lot of states. From 9 I go to the 7, I go to 1, I go on this side to the 5, and I go this side to the 10. So 9, 7, 1, 5, 10. So I have a set here: 9, 7, 1, 5, and 10. Okay, I should also write the commas in between. Okay, on epsilon I'm moving to these states. Okay, then on 7, again on A, B, and C I got nothing here, nothing here, and on epsilon 7 it's moved to the 1 and 5, right? So I move to the 1, comma 5. On 7 I move to the 1 and then move to the 5, right? Okay. Similarly from 1 I go to the, on A I can go to the 2. So on 1 I go to the state 2. Okay. Rest of these guys I go nowhere, and on epsilon move also there's no epsilon move. On 2, on taking input A I go nowhere, and on 2 on taking input B I go to the 4. Okay, 2 I go to the this, I go 4. So I will take right here 4, and there is no on transition on C, no transition epsilon moves. On 4 I go to the, on A I'm moving to nowhere, and this guy nowhere, this guy nowhere. But on epsilon on 4 I move to the 8. From 8 I can move to the 10. From 8 I can move to the 7 and 1 and 5. So they are all in the 4. So firstly on epsilon I can move to the 4 itself. So I have to write the 4 also. So it's a set 4, then 8, then 10, then 7, then 1, then 5. Okay, and now I will see the state 5. State 5 only moves on a C. So A, I go nowhere, B, I go nowhere, and on C I go to the state 6 as here. On epsilon I go nowhere, right? Then I have the 6 itself. 6 goes nowhere on A, B, and C. Only there is an epsilon transition. It goes to the 8, that goes to the 10, that goes to the 7, and 5, and 1. So we have on 6, firstly the 6. So this will be the new state for my DFA. 6, 8, 10. Then I go to the 7, right? 6, 8, and 10. From I go this path to the 7, 1, and 5. 7, 1, and 5, right? Okay. Now from 8, it's not necessarily you will make a transition table of this. You can make directly the Dfa transition table, but that becomes a little tougher. It becomes a little easier, right? So 8 on A, 8 goes nowhere here, nowhere here, nowhere here, and on epsilon it goes to the many places. So it goes to firstly 8, then to the 10, and if you go that way, it goes to the 7, then it goes to the 1, and it goes to the 5. It's again a new state for me, for the DFA. On 10, I go to nowhere, right? Whatsoever. So I go to nowhere, I got nowhere, I got nowhere, I got nowhere here. So even in epsilon, you can say here, because when I say epsilon, on the 1 goes to the 1, right? And 2 goes to the 2, and 5 goes to the 5. Because on epsilon moves, you can write yourself. You can go to yourself at least. Okay. Now we are done with the table here. Now we're gonna make the table in the DFA table out of this transition table, right? So it becomes much easier to make a DFA table. Okay. So out of this, I'm gonna make the DFA table where we say Nfa states, and we should understand the initial state is 9. So just the Q0. The first state, that's a 9. 9 is the start state, so that's again be the start state here. Now when we make the DFA table, we only make we see where we can reach. So we start from the first start state, and start state is not a single state; it is a set, right? And accordingly, we'll make our these guys, and I call it, maybe I can name it as an A. The state is called as an A, for example, right? So this thing is called as an A in my DFA, and I have to see where from I can reach from 9, 7, 1, 5, 10 on the A. Okay, so when I say 9, 7, 1, 5, 10, I have to see this also in my picture. Okay, 9, 7, 1, 5, 10 on the A, and you see on A I can only go to the 2 on when I have a 1, and I have 1 in it, right? So that means I go to the state 2 from this state, because this is my set. Out of this set, whenever I have someone which goes with an input, this whole group will go to that state, right? So it is going to the 2 only, right? And so I should write here the 2, but I call that, because this is a new state, maybe I call it the B. And what is B now? B is the 2, right? I write it here that I got a new state, I saw a new state, and I renamed it as the B. Okay. Okay. Now whenever I see the new state, I will start filling up here, and on B, and I see on the transition table on the B, I'm going to the only 4, and I have a 2. Do I have a 2 in it? No, I don't have a 2 in it, so I can't go anywhere on the state B. So what will be here? So I say, hey, I don't have anything, right? On C, and I see from this table, because now I don't have to look at it because I have made it here. Information is here, so I can go it very faster now. So on C, I see if I have a 5, I can go to the state 6, and I'm seeing that I have a 5 in it, right? So I have to go to state 6. Okay. But when I see the states, when I see here on A, the A on taking input A, small a goes to the B, that is the 2. And when I see the 2, and it doesn't have an epsilon moves, so it goes to 2 only. But here it's different. When it goes the 5 on taking the input C, it goes to the 6. But after 6, you can go to the 8, and you can go to the 10, and you can go from here to the 7, 1, 5. So actually on this you don't go to the 6 only, you go to the many places, and that new state I will call it as a C. Let me call that state as a C, capital C. Let me write that capital C here. And what else I have in that? I have all those states where I can reach from the 5 after taking input C. That is, I will have the 6 in it, right? Then 8, then 10, and on 8 I can go here, 7, 1, 5. So this new state will be 6, 8, 10, 7, 1, 5, right? So this will be 6, comma 8, comma 10, comma 7, comma 1, comma 5. So all these things will be called now the C. Okay, this will be called as a C now. Okay, so I am done with this. I can tick it. So actually I have to tick it up front. Okay, so that I mark it. That means I mark it that I have done it. Okay, let me mark it. Let me choose the pen. Maybe I will choose a red pen and say, hey, I have marked it. Actually I should mark it when I take it first. So I'm taking the B, I should mark it. Okay, now I will see where I can go from the B. B is only the state 2, where I can go from A and B and C. So if I see here in the transition table on A I'm going nowhere, so here I will be having dash, and on B we go to the 4, right? But where C is 4 having epsilon transition also, so on 2 on taking B, not only goes to the 4, but it can go to the 8, 10. From the 8 it goes from the 7 on 5. So that's going to be my new state. So here I go to the different set of states, and let me call that state as D. So I have saw the new state called D, right? So what is that D gonna be? So D is where you can reach from the B, which was in the NFA, the 2, state 2 was my in the NFA, right? So I have to see where I can reach from this 2 on taking the input B. So I can go to the 4, okay, firstly 4, then I can go to the 8, if you see the diagram, then I can go to the, from 8 I can go to the 10 on epsilon move, then I can go to the 7, then I can go to the 1 and 5 on that path if I take this path, right? 7, 1, 5. That's called as a D, because I saw the D, I wrote there here. There's a new state, that reachable state, and I'm writing it here, right? Now I have to see from the 2, if I take the C, I go nowhere, right here. So I go nowhere here. So I don't take it. Then after done, now I take the C ticket, mark it. Okay. Now I'm gonna mark it. Okay. Now after C, the C is actually 6, 8, 10, 7, and 5. And I have to see where I can reach from the A and the B and C from this set. Okay, 6, 8, 10, 7, and 5. So A, and I see from this table, A is only here, doing here things. Okay, if it is a 1, does it have a 1 in it? Yeah, it has. So it can go to the state 2. From 1 you can go to the state 2, and state 2 doesn't have epsilon transitions, so we can go only to the state 2. And what is state 2 called? State 2 is called the B, right? That means I go from C on taking input A, I go to the state B itself, that is 2, state 2 in the NFA. Okay, now after taking B, when I say the B, on B is having transition only on the 2. Has it 2 in it? No, it doesn't have, so I don't go anywhere. Then I will have the C. On the C has only on the 5. Does the 5 have here? Yeah, 5 is here, so I can go from here, from 5 I can go to C6, then I can go to the 8, then I can go to the 10 and 7 and 1 and 5. 6, 8, 10, 7 and 5. That is already done. That's called as C. So from C, if you take the input C, you go to the yourself only. That is, you go to the C only, right? Because you go to this set of state. That is that I called in the Dfa C. So that means if you go from this taking C input, you go to the yourself only. Now this is done. So we mark. Okay, so we're gonna mark it, mark the D, because we had. Okay, now from the D on the A is only having a 1. Is 1 here? Yeah, it is. So I have to move from 1 to the 2. So 2 is called the B. So I can go from D after taking input 1 to the state B. Now on taking B is having only on the 2. Is 2 here? 2 is not here, so I'm not gonna anywhere here, right? Okay. Then on C is having on the 5. Is 5 here? Yep, it is. So I go to the 6 actually, and 6, 8, 10, 7 on 5. That is already here. 6, 8, 10, 7 on 5 is called the C, right? That's called the C. So I should go to the C. Okay, so I am done. Now out of it I can make my Dfa transition diagram, right? So I got 4 states. Okay, firstly, my pen is not writing. There's some problem. Let me write it with the mouse. This is the first state. That is second state. This is the third state, and this is going to be the fourth state, right? Now the 9 was the initial state. That is, this is my A, B, C, D for example. Now this is going to be my the Dfa. Okay. There's some markers here. Okay. The firstly here, the 9 was the initial state, right? So 9, that 9 is in the A. So this is gonna be my initial state. And the final state in case of my this guy was the 10. So wherever there is a 10, okay, that is my actually the final state. So where is 10? 10 is in this, 10 is in this as well, 10 is here also. So these all 3 states, that's A, C and D, got up the final state. So as you see, double circles, A, C and D. And then it's very simple. On A you go from A to B and C, okay. From A you go to here, on C you go to the C, and similarly you take the diagram from this. From B you go to B, taking B go to the D, and from C you take A, go to the B, and you take C and go to the C itself, all that. And the D, from the A you go to the B, A you go to the B, and take the C here, you go to the C, right? So this is my equivalent Dfa, which acts the same language which Nfa was taking, right? So it was a little complex because we had a epsilon moves here. So it becomes very simple when we first make this diagram into the transition table. Then from this transition table we make the equivalent Dfa transition table, and we see we rename those guys, these guys, as A, B, C, D, and we make our Dfa. That's it. So this is our Nfa to Dfa. So why we converted this Nfa into Dfa? Because Dfa is something which we can implement, right? Both of these guys, Dfa and Nfa, or Epsilon Nfas, all accept exactly the same set of languages, okay? So we have 3 things. When I say the Dfa, then we said Nfa, and then now Epsilon Nfas also. So they take up the same set of languages. That's the regular language, right? But Nfa types are easier to design and may have exponentially fewer states than Dfa, because Dfa will have 2 raised by whatever states your Nfa has, okay? So it is exponentially lesser states of Nfa, and it's exponentially more states. But the Dfa only can be implemented, right? We can make a, because Dfa is something which a computer is like, so we have to convert this into the program. Now we can have a minimization of this Dfa as well, where we can minimize the states. It may have many states. We can minimize that. That's not a problem, and then we can implement that into make our final lexical analyzer program. Okay, so I think that's all for this now. See you in the next lecture. Until then, ma salama, and God bless you actually.